This lesson is going to be on potential energy diagrams, which is often abbreviated as PE diagrams. Now, what they do is they actually show the energy of the chemical reaction over time. There's a couple vocabulary words we need to talk about before we get started, and then I'll show you how to do the graphs. The forward reaction goes this way, the way we read, left to right. Reverse reaction does the opposite. So we're going to have to worry about forward and reverse reactions in this. So when we talk about forward and reverse, this is the direction that we're referring to. Activation energy is the minimum amount of energy needed to start a chemical reaction. Think of it like a barrier. It's going to be shown as a hill. If you don't have enough energy to meet the activation energy requirement, then no reaction happens. Here's the example I usually give. If you take a match and you strike it on the little striker pad that's outside the matchbook, if you don't do it hard enough or fast enough, you don't generate enough heat through friction to light the match. That heat and friction, that heat from friction is the activation energy. So in other words, if you don't strike it hard enough, then it's the head of the match or the tip is not going to get hot enough and then the match won't light. That's exactly what activation energy is. It's the minimum amount needed to make that match light. Catalysts. They lower the activation energy. They also speed up chemical reactions, and they're used in digestion. The main thing that we're going to talk about here is that they lower activation energy. And I'll explain that in a second. And then inhibitors. Inhibitors are anything that stops that stops a catalyst. In food science, an inhibitor is basically a preservative. So the bacteria that digest our food, that make our food go bad, they use catalysts in order to digest the food. Well, something that stops their catalysts will make the food last longer. We call it a preservative. That's really all a preservative is. Now, catalysts, they lower activation energy. So if we look at this, this is a PE diagram. So I'm going to explain everything. We have our reactants here, and we have our products here. Now, keep in mind, since this level here, there's going to be some number over here, represents the energy of our starting material. And then this number represents, or whatever this number is at, it would be all the way over here, would represent the energy of our ending material. So think of it like money. If you started with this much money, and then you ended with this much money, well, you lost money because the total amount of money you had went down. Don't worry about the hill in the middle. If you started here and ended here, the middle doesn't really matter. So that would be what we call exothermic, because we're losing money. If the hill, for some reason, looked like this, where you started here low and ended high, this would be endothermic. So an exothermic and an endothermic PE diagram are basically the same thing. You start on the left, you end on the right. It's just starting high and ending low versus starting low and ending high, absorbing energy or releasing energy. So now let's go to the actual hill itself. So the activation energy would be the energy needed to get from your starting point, which is right here, to the top of this hill. We call the top of the hill the activated complex. If you notice, there's two. So here's what happens. Under normal conditions, you would need enough energy to get all the way up here. Okay, once you're here, you go over the edge. Think of it like if you were going to roll a ball over this hill. If you don't give it enough energy to get over to this top peak here, then it's just going to roll back down. Whereas if you give it just enough to get here, it will then roll down the other side on its own. That is the activation energy. Now, what a catalyst does is it takes the size of this hill and it shrinks it. So this big hill, if you had a catalyst, would become this small hill. So if you notice, I have them labeled differently. The bigger hill I call the uncatalyzed reaction, RXN, pathway. The smaller hill I call the catalyzed reaction, RXN, pathway. I'm abbreviating everything here. So if you notice, I have two forward activation energies because there's the energy needed to get over the big hill, and then there's the energy needed to get over the small hill. So this big amount right here, from here to here, is the energy needed to get over the big hill, and this small amount right here is the energy needed to get over the small hill. Remember, we're starting from right here. And so this dotted line right here is an extension of the reactance level. So we have the forward activation energy with a catalyst, or I would just say catalyzed, and then you have the forward activation energy without a catalyst. I would say uncatalyzed. So there's two. Now, we also mentioned that there's forward and then there's reverse reactions. So it turns out there's forward and reverse activation energies. So you could think of it this way. If you're rolling a ball over this hill, if you're right here and you're trying to roll a ball over the hill, right? You've got this option and then you've got this option. They require different amounts of energy. But if you were here where the products are and you wanted to roll the ball over the hill in the reverse direction, well, then you'd have two separate size hills. There'd be the energy needed to get over this small hill, which is represented here, the reverse activation energy catalyzed. And then you'd have the energy needed to roll it over the big hill, which is represented here, the reverse activation energy uncatalyzed. All right, so that is what catalysts do. That is what activation energies are, and that's why on PE diagrams you'll always see two potential hills, because you have the uncatalyzed, which is always going to be the bigger one, and then you'll have the catalyzed, which will always be the smaller one. Now with this, abbreviations that I'm doing, I have a key here. This is how I'm going to be abbreviating it: reaction, FWD, REV, AE, PE, cat, and uncat, and here's what they all mean. So now let's look at a full PE diagram. This is what they look like. Okay, and I'm going to go over everything. Mine is color-coded. I want you to color-code and label yours as well. So we're starting on the left with our reactants. And our products are always on the left. Now the reactants and products can be represented literally by the words, or they could be a chemical reaction. So like, for example, if this was, let's say the chemical reaction was H2 plus O2 makes, I think it actually just makes H2O. And we'll balance the whole thing so it would look like that. So there's our chemical equation. Then this part, the reactants, would be this. And then this part would be our products. So you could represent them as the words, you could represent them as a chemical equation. Doesn't really matter. Now, we're starting here. The energy needed to get over the big hill, well, that's the activation energy of the forward reaction, because we're going left to right, uncatalyzed because it's the big hill. Then the energy needed to get over the smaller hill would be this one, the activation energy of the forward reaction, catalyzed, because the smaller hill is catalyzed. You could label the two paths, the uncatalyzed reaction path, the catalyzed reaction path. But notice, the forward activation energies, I'm using the same color because they're basically the same thing. The only difference between them is one is cat and one is uncat. So one is the big hill, one is the little hill. Let's go to the blues. They're the exact opposite. It's the energy needed to get over the hill from the other direction. So that's why they're called reverse. So they're both AEs because they're the energy needed to get over the hill. They are reverse reactions because they're going over the hill in the reverse direction. And then there's the cat and uncat. The uncat's the bigger hill, the catalyzed is the smaller hill. Don't worry about the red numbers. I'll explain what they mean in a second. Next thing we're going to label, potential energies. So now the potential energies are in green. If you notice, they have one thing in common. They all touch zero. So anything that touches zero is going to be a potential energy, zero being this line down here, the very bottom of the graph. So if you notice, only the green ones do that. All the other ones, they do touch a line, but that line doesn't happen to be like the product line here is not at 0, it's at 10, and the reactant line here is at 25. Those are just numbers I made up to do the next part of the example. So they all go to 0. So what do we have? The potential energy of the reactants, because this is the energy that the reactants have. It's from this line down to 0. Then we have the potential energy of the products. It's from the product line down to 0. Then we have the potential energies of the activated complex. Remember, the activated complex is the peak of the hill, which would be somewhere around there and somewhere around there. That's the activated complex. So notice I don't have the lines touching the dot. They don't have to. They just have to touch the height of the dot. So that's why having this line off to the side is totally fine, because it's the same height as the peak of the curve. Same thing with this. It's supposed to represent the peak of the curve. So these are the potential energies of the activated complexes. The big ones uncatalyzed, the smaller ones catalyzed. All right. And then the last part is the heat of reaction, which is the change in energy of the chemical reaction, which we learned about in our last video. So that is the difference. So think about it. If I started with $25 in my wallet, that's what these numbers are for, and I ended here with $10 in my wallet, what was my change in money? Well, you would take 25 and 10 and subtract. And that's what the heat of reaction represents. This difference represents the $15, which would be the change in energy in this case. So it would be kilojoules, not dollars, but whatever. And that's why the delta H is here. Now, granted, remember, these lines don't have to be in these locations. I could write this delta H anywhere along this column as long as it was showing me the difference between 25 and 10. So I could put it on the far left, I could put it in the middle, I could put it on the far right. It does not matter. Okay, it's about the numerical difference. And then the last part, the way you calculate delta H, we use the saying, some people like this, Pepper. It is the potential energy of the products, that's the PEP, minus the potential energy of the reactants. So in other words, delta H represents this value, 10, minus this value here, PE of the reactants, 25. And so if you get 10 minus 25, that would make your delta H would actually be negative 15. Because if you started with $25 and you ended with $10, then you lost $15. That's why delta H is negative. We also know that exothermic reactions, with which this is, have negative delta H signs. This is the reason why they have negative delta H signs. Last thing I'm going to mention is all the others. So the quantities that we're talking about can be represented two ways. They can be represented as literally this line, or they could be a number. In other words, what the AE of the forward reaction really means is it's the difference between the number that I'm at, in this case 25. I put these numbers in arbitrarily, so they don't mean they don't have to be 25, and the number at the top of the hill, which is 35. So the difference between 25 and 35 is 10. So this would be kilojoules or joules. It doesn't really make a difference. You could say that the AE of the forward reaction is this quantity as a line, or it could be numerically 25 and 35, the difference, which is positive 10. The positive negative doesn't really matter for these. It only really matters for delta H. So it's 10. The forward would be 40 and 25, which would be 15. PE of the reactants would be 25 to 0, which is 25. The same for the catalyzed and uncatalyzed activated complexes. The reverse catalyzed would be the difference between 35 and 10, which would be 25. This one would be 40 and 10, which would be 30. And this one would be from 10 to 0, which would be 10. So that's where the numbers come in. They can be represented both ways. This is what a exothermic reaction looks like. Remember, negative delta H is exo, and the reason it's exo, I told you, it's the final end money minus the starting money. That's how we figure out if we gained or lost money. And then the endothermic reaction, it's the same thing, except the curve changes. So if you look at the endothermic reactions, here's the big difference. In an endothermic reaction, the forward reaction, catalyzed and uncatalyzed, I use the same color, they're still on the left. Just now their size got much larger. So instead of being small values, they're the large values, because going over the hill from the left to right, the forward direction is now the bigger part of the hill. The reverse activation energies are now smaller in value because their side of the hill is smaller, but they didn't actually move. Forward is always left to right, reverse is always right to left. The PE of the activated complexes, they don't change ever. They're in the same spots they were, okay? The PE of the reactants is in the same spot it was, it's just smaller now. PE of the products, same spot it was, just larger. And then delta H, it's the same thing. It's the potential energy of the products. So in this case, the products is worth 25 minus the potential energy of the reactants, which in this case would be 10. So 25 minus 10 is positive 15. So this delta H represents the difference between these two, which could be represented as a line or it could be represented as a 15. In our last diagram, I had it off to the side. I had it over here somewhere. I shifted it a little just to show you. It's not usually drawn. It's traditionally drawn in the middle, but in reality, I could put it here, I could put it here, I could put it here. It wouldn't make a difference as long as it represents the difference between 25 and 10 for this particular graph. It could be drawn anywhere left to right. Okay, so that's the only real differences. Now, if you think about this in terms of learning these values and memorizing them, they're not that bad because there's these two, or the forward activation energies are really one thing because there's cat and uncat. The reverse are really just one thing, cat and uncat. The two activated complex potential energies are just cat and uncat. And so it's really 1, 2, 3, 4, 5, 6. There's 6 things to learn about this graph, and that's really it. And then they expand a little bit. So that is PE diagrams.